Hi everyone, in the last video we talked about namespaces and assignments. In this video I want to look at the programming part of that and how namespaces look while we are programming. First of all, there is the dir function like this, which prints us the entire namespace dir is called in. So this is just dir called in the global namespace, so all these names that you see here in this list are part of the global namespace. And when we assign a name here to a value like this, we create this name in our namespace. You see here at the end, the name string is now part of our namespace. Now this is the namespace part of it. We also talked about the fact that names refer to actual objects in object space, and we can visualize that with the id function by calling the id function on the name we just assigned, and this gives us a number. And this number is not particularly informative, but it will be today, but only for educational purposes. Looking at the documentation of id, we read that id returns the identity of an object. And it also tells us this is guaranteed to be unique among simultaneously existing objects. CPython uses the object's memory address. So this is the actual place and in its integer representation where the object lives. And this is the object that the name string refers to. Now what happens when we assign string to a different object? Let's assign it to Bob. Of course the ID has to change because, as we discussed in the last video, strings are immutable. So we cannot have changed the actual value of Jeff, which lived at this particular place in memory. What we did instead is we created an entirely new object, Bob, that has to live in a different place in memory. And it is so that we get a different name. Excuse me, we get a different number here, because Bob is a different object. Now let's do that again. Let's start again with Jeff. Let's look at his ID. And what happens now when we assign a different name to that same string? Now we have the name newString and the name string, both referring to this object Jeff. That of course means that now both names refer to the same object, and this is manifest by here we see the same number. And you have to keep in mind the documentation of ID tells us this is guaranteed to be unique among simultaneously existing objects. Now you might say, well, it's not really unique, is it? It is not unique for different names, but it is unique for different objects. However, this is not a different object, it's exactly the same object, the object Jeff. Now what happens if we change string to Bob? We of course get a new object, but the new string is still referring to Jeff. So new string remained unchanged. Now let's look at the upper function. Let's start again with Jeff assigned. Let's verify where it lives. And now we call string.upper. And as you might remember, string.upper gives us the all uppercase representation of a string, like this. But nothing changed. And nothing changed because this upper function is unable, it cannot by design change the value of the actual object Jeff. Nothing changed here. It's still the same string as before. It's not this one. What we have to do if we want to actually get a new string that is all uppercase is we have to assign the result of upper to a new string. And now we can see those are entirely different objects. They both live at different places, and of course string itself remained completely unchanged. So this is all fine for immutable objects, such as strings. Strings are immutable. Now, my lists are mutable. We can change them, as I showed last time. First, we have to remember list lives at a certain place in memory, but each of its individual components lives in a different place. So what we can change is the actual my list. But the fact that my list is changeable does not change the fact that whatever lives at these individual places might be unchangeable. And in fact, integers are not changeable. They are immutable. So the fact that my list is mutable doesn't change the fact that its individual components are immutable. And we can see that by assigning another value to the second index of my list. And what we will see is that my list is still the same object. It's still in the same place in memory. The same goes for the value at the index 0, but this value here has now changed. So this first index now refers to a different object. Now let's look at the example where we try to keep a copy of our old list before we change it. Let's again look at the ID. Now we want old list to keep my list. But if you've seen my last video, you will remember that it doesn't quite work like this. The problem we have is that my list and old list both refer to exactly the same object. So if we change exactly that object, we change both my list and we change old list. Both of these have changed now, but both of them still refer to the same object. Now when we try to change immutable objects, Python automatically gives us a copy instead of the actual object. So what we need to do with mutable object is we have to make our own copy, and we have to do so explicitly. So what we have to do is we assign old list to mylist.copy. And now, of course, mylist and old list don't refer to the same object. Old list refers to a different object, a copy that was made in a different place in memory. So now when we change mylist, when we change the second index of my list, we change, but old list remains unchanged because it's not the same object. Now finally I want to talk about the is keyword. The is keyword is a boolean operator. When we program in Python, we usually don't use these ID numbers. Python is not written for us to do things like pointer arithmetics or to actually work with the location in memory. Python is built so that we can entirely ignore where an object lives. But what we need to know is if an object is mutable or immutable. And when we deal with these different types of objects, we sometimes want to know if two names refer to the same object. And that is different from the equality operator. So the equality operator will only check if two objects are identical by value. Now mylist and newList, Because I assigned new list to a copy of my list, they're both different objects. But if we compare them by value with the equality operator, we get true. Both of them have the same value. They look exactly the same. But if we use the is keyword, we will see that the is keyword will return us false. And that is simply because both of these names refer to objects that live in different places in memory. They are not the same object. Now, when we assign new list to my list, like this, without calling the copy method, and now we try the is keyword, we will get true, because they both refer to exactly the same object. So the is keyword gives us a stronger form of equality. It's not just equality by value, but it's equality by location in memory. And of course, if two names refer to exactly the same object in memory, their value has to also be identical. So if the is condition is true, the equality condition also has to be true. However, if we have two different objects, so the is condition is false, they can still be equal in value, as is the case whenever we, for example, make a copy, but objects can be equal for different reasons. So this wraps up our namespace discussion for today. There's a lot more to say about namespaces later on, especially when we will talk about concepts such as scope. As it turns out, namespaces can exist within other namespaces, and this will be very important at a later point. However, for now, I hoped the discussion about assignments and how assignments are related to namespaces can help you understand better why your code does the things it does. The take-home message is that an assignment creates a name in our namespace and this name refers to an actual object in memory. Now that's it for today. See you in the next video.